Yeah, thanks a lot for the introduction. Thanks to all of you for having me here. Yeah, I must say UCLA became a kind of second academic home. Tried to count and babbling here how many times I've been here already, and I got stuck somewhere between number 4 and number 6. Yeah, today I want to give you some flavor of our research line done in collaboration with Eric here and Martin Hidding, former postdoc in the Uppsala group. So we last year arrived at a paper where we constructed polylogarithms on higher-genus Riemann surfaces. And the goal is to not only talk about the specific results in that paper, but also to give some general context, hoping to motivate why it could connect with your research of everyday life. Yeah, so this is admittedly a mathematical subject, how to deal with integrations on non-standard geometries like higher-genus Riemann surfaces. And accordingly, we benefited a lot from some work done in mathematics. So here are 3 papers in the math literature that were particularly influential to us, done by Brown and Levin for elliptic polylogarithms. And then more recently, Enrique Stervini about our higher-genus Riemann surfaces. And also we start to learn about an important paper that Enrique wrote in 2011. Yeah, what is this talk about? In a nutshell, this is about your pipe dream from high school, where you learned about differentiation and integration. You were probably told that differentiation is comparably easy, that you will always succeed by applying a small number of rules, a la Leibniz and concatenation and so on. Differentiation was easy and under control. However, integration was in general hard, and you need a lot of guessing power to find a convenient substitution rule for your integration variables. So integration in general hard, if not undoable. And this talk aims to go a step in making integration more possible or even algorithmic, as long as the integral in question lives on the right geometry. And here we try to take the step from the sphere of the torus all the way to a higher-genus Riemann surface of arbitrary genus, which looks somewhat like that. And for the experts, you don't even need to be in the hyperelliptic divisor, like for any shape or any complex structure moduli of that surface. We aim to say something about the integrals you can define on it. Yeah, so the goal is to construct a function space which helps in various areas of physics, in any area where you need to integrate. And the kind of function space we have in mind, it resembles the polylogarithms, which I hope some of you have seen at genus 0 and genus 1. Why do we like polylogarithms? It's some kind of adaptive function space, which is large enough that you can get any integral of a rational function done, or iterated integral over rational functions. But it's at the same time controllable. It's not excessively large, but it just has the right size that you can work with it, get anything integrated on the sphere, but still you can control the properties, like deciding if 2 expressions are the same or different, or controlling numerical evaluations. And similar amount of control has recently been obtained at the elliptic case for elliptic polylogarithms, which are iterated integrals of a torus, like the genus 1 instance of this Riemann surface up here. And yeah, so for the elliptic polylogs, I was mostly using them in string theory contexts in my research. I can really say that it's quite great to have such a function space and the help of mathematicians to study it. And then also in Feynman integrals, the elliptic polylogs, I dare to say, were game-changing over the last 10 years to get a lot of Feynman integrals evaluated, even have numerical access on it, even though they were previously out of reach. So just to give some examples, the sunrise diagram with generic masses is elliptic, or more recently, a student in the Uppsala group with his collaborators in Bonn and Brown University evaluated the kite graph with generic masses. So as long as the internal lines are associated with generic masses, then you need elliptic polylogarithms to nail these Feynman integrals. Okay, it's motivations like that drive the question, what to do if the Riemann surface has genus larger than 1. And indeed, there are plenty of Feynman integrals where you find yourself with a higher genus Riemann surface. And in string perturbation theory, it's even by definition that in order to control string amplitudes at H loops, you start by drawing a genus H Riemann surface, and then at some point you need to perform integrals over the moduli. namely marked points in case of string amplitudes that represent the external states. And also in string amplitudes, you need to integrate over the moduli, over complex structure moduli that tell you about the shape. So in one way or another, many people in high energy physics want to do integrals in a higher genus Riemann surface sooner or later. And yeah, my goal is to describe a possible organization scheme for those iterated integrals at genus 2 and higher, beyond the reach of the elliptic ones. I really try to spend a lot of time on the genus 0 and genus 1 review, just to get everybody on the same page. And as far as time permits, I will get to the main results of the paper to tell you about the generalization to higher genus. Maybe to throw in some semi-technical buzzwords. The construction will proceed by finding a so-called flat connection, something that obeys an integrability condition, which in the simplest case is a Clichy homological form for CFT practitioners in the room. And the main reason why these polylogarithms have been useful so far at genus 0 and genus 1 was they were closed undertaking primitives. You would always be able to integrate over marked points on the sphere or on the torus within the realm of genus 0 polylogs or their elliptic analogs. And in case of our higher genus fellows, we do have a lot of supporting evidence that they will close undertaking primitives, but we are still working hard on giving a proof for that conjecture. So whenever you see me discussing with Eric over the next days, maybe it's related to this challenge where we are making good progress at the moment. Yeah, I will start with genus 0 to give conventions and to give a flavor of how the formula look like that connect with all these general words. Are there any general questions before going into genus 0? Okay, then part 1 of the review is genus 0. Then let me try to get straight to the point for those who have worked with multiple polylogarithms at genus 0. So multiple polylogarithms are functions of many complex numbers, denoted by A or by Z. And the last one of those was telling you about where you perform an integral. And the integration kernels are always rational functions. So one of these entries tells you about the latest integral you can do. And here I give a recursive definition of polylogs. The number of A variables, W, sometimes called the weight, it tells you how many integrations are hidden. So on the right, this is of lower weight. And the clue is that you integrate over the last variable and decorate it by a rational function. Okay, so since this is a recursion, I better give you a starting point for that recursion. It all recurses down to the empty word, where this polylogarithm is defined to be 1. And maybe a more interesting case is if you do a single integration, like if you have a single A variable, and then this is the old school logarithm in this way. And then everything else goes into dilog, trilog, and in general, it's a little bit larger than only the LIN functions. So some people use an LI notation with multiple subscripts to give an alternative description of this. Okay, these are the ones that I referred to before as having enabled a lot of progress on the Feynman integral side. Yeah, and also in string amplitudeology, they were pretty useful at genus 0. Okay, now one way to organize this infinity of polylogs is to package them into a generating series. Maybe this is not always obvious why generating series are good ideas. Maybe your problem only requires a given upper limit on the weight. Maybe in that case, you're not so interested in a generating series. But for the elliptic case and for higher genus, it's really important to repackage this in a generating series. That's why I do it here to give you a first flavor of how the higher genus formula will look like. And throughout this talk, there will be plenty of path-ordered exponentials, which are defined as follows. If I integrate over exponential like such, then this path ordering symbol P instructs you to do the following. So up to the linear order, it looks like this is an ordinary exponential, but starting from the second order of expanding the exponential, you see the impact of the P prescription. Well, you will bring down 2 powers of that integrand or connection J, and you make sure that connections at later points are standing on the left compared to connections of earlier points x1. And there are similar iterated integrals over some sort of simplex if you expand to higher orders. Okay, so this notation is defined here. And for genus 0, we make a specific choice for that connection. So in order to generate some of the above polylogs, let's specialize J to be the so-called Chnishik-Samolotchikov connection. Let's plug in this, where we put in 2 samples of the integration kernels here. These are integration kernels with a equals 0 or a equals 1. And to make sure that we can access all these polylogs individually, let's put some non-commuting variables, E0 and E1. Let's just say they don't commute with one another and satisfy no relation among words E0, E1. Or in more formal terms, there is a freely generated Lie algebra spanned by E0, E1. And the path-ordered exponential lives in the associated group, in the universal enveloping algebra of Lie, E0, and E1. So the notation is like that, when there's a freely generated Lie algebra. And it just means the intuitive thing. You can read out separately the coefficient of each word in these E0s and E1s. And yeah, FGLA is my acronym for that. Good. How does it look like in the specific case of the KZ connection? Let's take that starting point of the integral to be the origin, and then that path-ordered exponential lines up with the definition of polylogs. So not surprisingly, the first order just gives back something like that. This is just the ordinary logarithm. And depending on what you put in the first place, it's decorated either by E0 or by E1. And yeah, if you go to higher orders, you can see that you get polylogs in one variable, where all of the A's are constrained to be 0 or 1. So it's really about binary words, 0 or 1, or E0, E1. And I hope it's pretty obvious how that goes on. And if you insist in doing polylogs in multiple variables, then of course you can put in more terms into the connection. So nobody stops you from adding a term, for instance, EY divided by X minus Y. So there's nothing fancy that kicks in if you want to have a multivariate generalization of that. Okay, now let's get to the notion of a flat connection. We want to view this as a function of the marked points and definitely not as a function of the path. There shouldn't be any need to tell you how I travel from 0 to x. So we want these integrals to be homotopy invariant. And formally speaking, what do I need to impose on J such that the integral is homotopy invariant? So it's only a function of the endpoints of the path if the connection is nice enough to obey the flatness condition, if the connection is flat. So in general, flatness means take the total differential in the integration variables and then dj should be identical to j wedge j. Okay, so this is the flatness condition in general. And let's check how it works out in the Cauchy-Samolotchikov case. And well, it's pretty lame. Both terms are individually zero. The KZ connection is enthusiastically flat. I mean, you don't see any x bar. So immediately dj is zero. And also, since it's proportional to dx and has no dx bar, also the second term is zero. So here, the genus zero case, maybe it's too boring as an example, but we will already see in genus one that there, the connection of Brown and Levin is not flat term by term, but you need to go through the interplay of both to see flatness of the Brown-Levin connection.
But even if you have multiple variables, you would have a non-trivial addition. How about genus zero?
Okay, sorry, you mean?
You have multi-variable,
Yeah.
x, dy, and second term is a non-zero.
Oh, actually, I would still keep the dx up front. So here the viewpoint taken is we are on the configuration space with marked points on the sphere, and I go to the filer where I only integrate over one variable. So x is the integration variable, and all the others are spectators, like y, or you can put more. Yeah. But of course, it's a follow-up question how you can change vibration basis. So there's definitely some technology on the market that I'm not reviewing today. If you want to have several variables and make them change their role, whom you integrate fast at first. So there are a lot of nice properties of polylogs investigated by Brown and many others that eventually you can switch gears and integrate over y instead. Okay, I will now move on to genus one, unless you want to ask more about genus zero.
So you also removed the points, right? 0 and 1.
Oh, yeah, indeed.
You really have a delta function or something on the side.
True, yeah. So this is, if you wish, about the puncture sphere with these points removed, or potentially further points removed.
Yeah.
I mean, here we are already in an SL2 gauge where one of the points has been moved to infinity. Right. That's why you don't see it in the formula. But genus one, let me tell you about the Brown-Levin definition of elliptic polylogs. Yeah, and admittedly, there are several alternative formulations of elliptic polylogs. So those who like the polynomial description of an elliptic curve, y squared equal degree 3 polynomial in x, may not recognize the objects on the spot that I'm writing down. So this Brown-Levin formulation that I'm reviewing is more tailored to the torus description with Jacobi theta functions being the natural functions of marked points. But there is work to translate into the polynomial description. Don't hesitate to approach me after the talk to give you references for that. Okay, and this Brown-Levin connection, it again lives in a freely generated Lie algebra. Now the non-commutative variables are called A and E. They have some commonalities with E0 and E1, but also some conceptual differences, as we will see. But perhaps I first give you an expression and talk about what it contains. So I highlighted that the KZ connection is so simple because there's no reference to X bar. Unfortunately, this is no longer the case at genus one. Now I need a connection where flatness is non-trivial. And yeah, one of the non-commutative variables, little b, it enters through repeated adjoint action. So we have a non-commutative A variable, and I throw a couple of adjoint actions on it. There's a function omega that I will introduce shortly, but it's safe to say already now that this has a Taylor expansion around the origin with respect to the second argument. So you can read this here as A plus single adjoint action and second adjoint action. So it's a power series in at B. And there will be some coefficient functions. that you will meet in the next minutes. So these are, to say it straight away, integration kernels at genus 1 that are in one way or another an uplift of these rational kernels from genus 0. Okay, and why am I working so hard to introduce an X-bar dependence? So this aims to be a connection that lives on the torus. Means there should be two periodicities as I walk around the A cycle or the B cycle of the torus. Just imagine the Riemann surface ends here. There are two periodic directions. And in my favorite parametrization of the torus, this translates into two periodicities. I can shift the mark point X either by 1 or by tau. And maybe I should just draw the parallelogram that I use to parameterize that surface. So here we are on the complex X plane. And one of the periodicities is here. So this is, without loss of generality, the A cycle. But I also need a second periodicity for the B cycle drawn in green. And this is the periodic direction going from 0 to tau. And to close the parallelogram, there's this fourth point, tau plus 1. Yeah. So that connection is constructed to be doubly periodic. So it's an honest function on the torus and not on the covering space. Good. So this is the general setting, and let's now talk about the function theory here on. What is this mysterious omega? This is known as the Kronecker-Eisenstein series. So if you wish, a collection of spanning integration kernels. So here, as a function of two mark points and a modular parameter tau, it is, roughly speaking, a ratio of theta functions. In order to be self-contained, I've spelled out the definition of a theta function on the board, but you don't need to be an expert on these animals. So even if you haven't seen this definition before, I think the only thing you really need to know is that close to the origin, it goes like a linear function. So close to the origin, replace it by something proportional to z plus order x cubed. It vanishes linearly at the origin. And in that sense, it has the same singularity structure as the kernels in here. I mean, at genus 0, we were looking at dx over x to produce logarithms. And the key point is to have a pole, dx over x. And similarly, this object is engineered to have a simple pole. It goes roughly like 1 over x. But I need to embed this to the periodicity properties of the torus. It's not so easy to do 1 over x, but being at the same time doubly periodic. And for that reason, we need the help of many theta functions, and we even need to introduce a second variable alpha. And furthermore, we need to go as far as introducing a non-holomorphicity in X. I mean, we want to be doubly periodic, and this is a pretty tall order. In order to write down doubly periodic functions, quite often you're forced to go non-holomorphic. And if you only want to have a simple pole, then and maybe meromorphic, then you will violate the double periodicity. So it's really a delicate balance. And here the solution of Brown and Levin is to just learn to live with a mild non-holomorphicity. And there are a few x bars in here, but well, it's something pretty simple. Exponential of x bar, well, it's not that bad. Okay, we use this as a generating series for the kernels in here. And now I do something slightly perverse about the alpha parameter. I mean, it looks like that alpha is also a mark point on the torus. Typically, when you see something in the first argument of a theta function, you are tempted to interpret it like a mark point here. But what I do is, I Laurent expand in this alpha variable. So let's use this alpha expansion as a generating series for a couple of kernels, dot Fn, and they are individually doubly periodic. I mean, for each value of alpha, this is a doubly periodic function of z. But that's a generating machine for doubly periodic integration kernels. Yes. So this is how these leading terms come about that I already previewed. And let me be completely explicit what the first f function is. I already advertised it for its simple pole. And if you go through that ratio of theta functions, then you will find that it goes like that.
This construction seems very unobvious. I mean, as a generating function.
Yeah.
And the last thing you did, theta, you build a generating function, but here, how did they know, or how did?
Okay, let's say a tempting solution is to stop after f1. Then you have the simple pole you want, and you're doubly periodic. However, the flatness condition forces you to go higher. I mean, if you look at the flatness, you will at some point take an x bar derivative. And in order to obey the flatness condition, you need to exponentiate something. Yeah, so an alternative way of looking at it is to leave it out and to look at the monodromies around the B cycle. And you want these monodromies to be multiplicative rather than additive. There are several ways of looking at it, but in one way or another, you will violate a key property that you want if you cut off that infinite series. Yeah, maybe I should say this right now, that flatness is non-trivial here. It works out at the end of the day that the total differential of this Brown-Levin connection x it's equal to j wedge j. I mean, just to be clear, we only differentiate in x here. We do this at fixed tau. We're not differentiating in the moduli. But yeah, in order to satisfy this, it's something like an anti-holomorphic differential equation. And this only works out if you really exponentiate the x bar dependence. Or saying it in a different way, also the closure condition under integration, also this fails if you stop with f1. So I admit, it looks like there are many blind passages, like the higher order integration kernels. They no longer have a pole, but you need them to obey the integrability condition. And this was the most basic motivation. You want a function space that unconditionally closes under integration in X. And yeah, so as I was saying in words, this comes about from the differential equation in X bar. This is the backbone of why that integrability condition is satisfied. And this works because that Kronecker-Eisenstein series omega obeys this differential equation here. Okay, since the connection is flat, we can now use its path-ordered exponential to generate the desired polylogs. And now the path-ordered exponential will be valued in the a and b's as non-commutative variables. So now you can read off one elliptic polylog from each word in a and b. So same prescription as before, put the connection into this path-ordered exponential. And what you, for instance, get is some function associated with one letter word in A, then another function coming just with a one letter word in B. But of course, this goes over arbitrary words of arbitrary lengths. So if I write this a little bit more formally, this is a sum over all words W that are formed from the letters A and B. I guess mathematicians would write this curly bracket to the power X in order to state that words of arbitrary length are part of the club, starting with a trivial word, going along with one letter words and anything higher. And yeah, to each word, I can read out the coefficient, and that's going to be a homotopy invariant iterated integral. And these are the Brown-Levin elliptic polylogs. So admittedly, you will find a bit of non-holomorphicity inside the integrand coming, for instance, from here. But this is a well-calibrated construction. If you catch everything that goes with a given word in A and B, all the non-holomorphicity conspires to give you a homotopy invariant iterated integral. So it's at a generating series level clear that homotopy invariance holds for an arbitrary word in these A's and B's. Now, in particle physics literature, you may have met a different description of the same function space. For instance, some symbols that are also denoted by capital gamma, but have a twiddle on top. These are, for instance, used by the group around Clodua. And these gamma twiddles, they use a meromorphic connection, omitting that. Then the price to pay is that you no longer have kernels that live on the torus, but nevertheless, you span the same function space. And these are then turn-by-turn meromorphic. That's possible and successfully used. And it goes all the way to having software in the market to evaluate these things numerically. Yeah, and also these fellows here can be relatively easily reduced to the gamma twiddles in the literature, and hence can also be evaluated numerically. Yeah, the reason that I'm insisting on this construction here is that from today's viewpoint, this one generalizes more readily to higher genus. So we currently don't know what the higher genus analog of the meromorphic gamma twiddles is. Okay, yeah, the transition to higher genus is approaching, but before doing it, let me tell you about the double life of these integration kernels F. So I just defined them in a rather baroque way by writing down theta functions and asking you to expand. But there's an alternative way to get these doubly periodic F kernels. Okay, and this is the one which, from today's perspective, generalizes more smoothly to higher genus. So in this alternative description, you start with the torus-Green's function that you can get from string theory textbooks, maybe Polchinski or others. So as I told you, this theta1 function, it vanishes linearly at the origin. And hence, this expression here is essentially log of z squared. And this is what you want from the Green's function of the free boson on arbitrary surfaces. And to make sure that this is well behaved on the torus, we again need a doubly periodic completion. And same story as before, in order to be doubly periodic, you sometimes have to swallow a pill, such as introducing these non-harmonic terms here. This is the doubly periodic completion. Without it, you would be in trouble to have the B-cycle periodicity. Okay, and once you're comfortable about this closed string Green's function, then you can go ahead and construct all the ingredients in the Brown-Levin connection from two kinds of operations. First is take a derivative. If I have not wiped out F1, then this is something you could check in real time. The F1 function, which was d log theta, is nothing but the derivative of the torus-Green's function in the first argument. So this settles the, well, first non-trivial term of the Kronecker-Eisenstein series. But now all the others, they require one more operation, namely convolution. Let's now do integrals over this F1 or torus-Green's function. And the fine print goes as follows. We integrate over the torus, roughly speaking, over the parallelogram. And then from convolutions, you can build up a recursion. All you need is f1, and you can build up f2 by integrating f1 against f1. So this holds for all n2 or larger. Okay, so these f kernels have the pleasant property that they're closed under convolutions. Maybe this is not the same kind of integrals that you want to do here. I mostly talk about iterated integrals along a path, but as a nice aside, they also behave nicely under two-dimensional integrals when you integrate over the surface. Yeah, this is an important fun fact about the F kernels at genus 1, and it's a key property that opens the gate to higher genus. Yeah, so this brings me to the end of the review chapter. And I would next go to higher genus. But it's a good moment to ask questions. Don't be shy, please. Okay, so what comes next? So a couple of basics. Well, there's still the picture of a higher genus Riemann surface. The homology is 2H dimensional at genus H. There are many homology cycles, and I can arrange them into pairs, namely a couple of A cycles, H of them, and furthermore, the same number H of B cycles. And one can arrange them in a way that they have a canonical intersection, that the AI cycle intersects nobody other than the BI cycle. So we work in this arrangement of the homology. And after clarifying homology, then the next question concerns cohomology. Whom do we integrate? And it all starts with abelian differentials that are, in a loose sense, the higher genus versions of dx. And there's not one of them, but it's a total of H abelian holomorphic differentials that are well defined in the surface. And one typically makes a basis choice that is resonating with the cycles above here. Let's say we normalize them on the A cycles in the sense that this integral here over the A cycle of omega j is a chronicle. Okay, then you have in some sense exhausted your freedom to do basis change for the omegas. And then for the B cycle integral, you can no longer control the outcome. And this defines the period matrix. It's symmetric if you take a closer look in its two indices. And for genus 2 and 3, these are exactly the complex structure moduli, or in one-to-one correspondence. There are a couple of subtleties starting from genus 4, but I will loosely refer to these period matrix entries as the moduli. So this generalizes the tau that you have seen at genus 1 for the torus. Okay, so these are some basic ingredients that we will combine to build up a connection similar to the Brown-Levine one. Then what else do I need to introduce? Some shorthand notation. The analog of all these inverse in taus that you have seen here and there, we will use following shorthand notation. Instead of an imaginary part of tau, I will encounter, well, the imaginary parts of this period matrix, and I will use its inverse to raise and lower indices. And sorry, inverse is only raising indices, not lowering. Okay, so whenever you see a y upstairs, then it's the inverse of the period matrix. Okay, and that will be a shorthand I'll use here and there. I need to tell you about how typical surface integrals work. So a lot of them you can do with the Riemann bilinear relation. If you integrate over the surface a volume form with a holomorphic abelian differential and a complex conjugate one, This is a bit the analog of doing the surface integral, computing the surface of the torus. But now at higher genus, you have these free floating indices. So you need to be careful which of the abelian differentials you take and which of its complex conjugates. So it's really an H by H matrix full of volume forms. And a particularly nice one is the so-called scalar form, denoted by kappa, which is a certain contraction of these omegas that goes like forwards. Okay, sorry for this boring shower of definitions. Now I'll try to go back to the track of constructing iterated integrals and connection. Yeah, so I want to follow the path of what I just wiped out at genus 1, give you a Green's function, and then give you some operations to do on the Green's function to build a connection, to build integration kernels for higher genus polynomials. And yeah, the particularly useful Green's function that we used in our paper is the Arkelov one. There's some other literature on it, maybe going all the way back to Faltings and 84. And I think the place where the Arkelov Green's function entered the string theory literature is in this paper by Eric with Michael Green and Boris Biolin. Or maybe some of your earlier works were taking a first look at it. But here I found the nicest library of properties and identities. Yeah, so what I can tell you about this Arkelov Green's function is that it's the higher genus analog of this torus Green's function that you saw before. This was that d log theta 1 and so on. And in order to construct it explicitly, we have to proceed in 2 steps. So an intermediate step is sometimes known as the string Green's function, which takes a d log of theta 1. And maybe the experts in the room know that the theta 1 function generalizes to the so-called prime form at higher genus. So this is again something that vanishes linearly at the origin, linearly in x minus y. Just approach me after the talk if you want to see definitions and all that. And then we need doubly periodic completion. And this requires some analog of the im z squared term that is unfortunately wiped out, but not a big deal. You can see it from here. So this already eliminates some monodromies. And then the last step, the last embellishment that you need to do on the Arkelov Green's function is you want to make it single value, 2 copies of the surface. And in particular, you want to have a good Laplace equation. And that requires some subtractions. You want to enforce the following property. You want to enforce that the Arkelov Green's function integrates to 0 with respect to the canonical form kappa. So that's why I really needed to go through a couple of definitions over here. So this kappa form, where is it? Also known as the scalar form. Yeah, it's, say, a particularly canonical volume form. And you need to impose this property in order to have a single valued Green's function. And sadly, this is not yet true for the string Green's function over here, but it's almost straightforward to enforce that. So you can enforce that condition by subtracting integrals, by saying you start from the string Green's function, the prime form and some abelian integrals, and then you subtract integrals of that string Green's function. By itself, it does not yet integrate to 0, but you can almost trivially enforce that by making some subtractions like that. So when the dust settles, you get a single valued Green's function, the Arkelov one. And this is something you can trust in the construction of a connection and in building convolutions. And when we check the flatness of the connection, like the anti-holomorphic derivatives of the Brown-Levin case at genus 1, we also need some information about anti-holomorphic derivatives or Laplace equations. And yeah, you can check with that Arakelov-Green's function that it has an integrable Laplace equation, and which can be used to later on demonstrate flatness of the connection. Okay, so my apologies for those who haven't seen these objects before. So this aims to be a lightning crash course on what kind of gadgets are worth manipulating on higher genus surfaces. And I really insist on single-valuedness of the Green's function, because in the next step, I will compute integrals over it. And I want these integrals to be well-defined. I mean, don't even think about integrating a multi-valued function. And yeah, this is a necessary condition for well-defined integrals.
So is this Arakelov-Green function related to the Arakelov geometry and Green function there?
Okay,
I'm just
I think it is, but I don't know the literature well enough to give you a qualified account.
yeah. So there's a Green function in Arakelov geometry that essentially counts points on a geodesic and so on.
Oh yeah, I think this has been used to define a length or a distance.
Yes.
In geodesics, yeah.
Okay, so it's like
Maybe Eric can give a more qualified answer.
Well, I think what occurs at the Arakelov-Green's function involving, for example, is actually the exponential function, or exponential minus g. So it vanishes when x comes close to y, and it's essentially a norm of divisors. That's its role. But it's so we call a Green's function for us is something that satisfies some Laplace type equation, right? While Faltings uses it for its norm, so we just abuse the notation a bit and call this the Arakelov-Green's function. But yes, it's intimately related to that.
Thank you.
Good. Thank you, Eric. Okay, I was advertising it for its suitability to be sticked into an integral. So let's do that. We want to construct integration kernels for a connection via convolutions. So just to be clear on where the journey is going, this is in order to define a higher genus variant of the Kronecker-Eisenstein kernels, which were ubiquitous in the elliptic case. So let's start with a modest question. What about the F1, which used to be just the Z derivative of the torus Green's function? And well, derivative of the Green's function is good, but it's not the only component. So in fact, already the F1 uplifts to some 2 tensor, where I need 2 indices that range from 0 to h. From 1 to h. So now that there's more than one pair of A's and B cycles, there are free-floating indices all over the place. You saw a couple of samples already. And it's exactly the same for the integration kernels that we built from convolutions. Okay, so there is, as promised, the derivative of the Arakelov-Green's function. And that is, so to say, the diagonal of the tensorial F1. But in order to get a good Laplace equation, or later on the flatness, we need some extra terms. And these are functions of one variable. This phi tensor was firstly used in the mathematics literature, the work of Kawazumi, and Eric and friends used it in string perturbation theory to perform low energy expansions. So this is an integral over Arakelov-Green's function. And at genus 1, I could not write that down, because at genus 1, this is the canonical volume form, and the Green's function integrates to 0. So this is trivial at genus 1, that's why we didn't see it before. But from over here, I only impose the Green's function integrates to 0 against kappa. So the trick here is to replace kappa by a more generic volume form. As long as these indices here are not contracted, that integral is non-zero and gives rise to this funny pi tensor over here. Okay, so this is a tensorial variant of the F1, and it again has a simple pole at the origin. So to maintain the genus zero intuition, we are integrating simple poles. Then let's keep in mind that the singularity structure goes like Kronecker delta divided by that. So it's still about integrating simple poles and having logarithmic singularities. But everything is embedded in a setting where the connection is single valued on 2 points on a higher genus Riemann surface. And what I failed to stress before, we used to have translation invariance at genus 1. So we were only looking at functions of x minus y at genus 1. But this is no longer the case at genus 2. We are losing translation invariance. So this is intrinsically a function of 2 mark points and not only of their difference. That's why I try to be very cautious and not writing any x minus y's here. Then if there was more time, I would furthermore tell you about modular properties. Well, I didn't even discuss the modular group of genus 1. Imagine you permute the homology cycles in a certain way. Then theta functions have good properties. And in particular, the Brown-Levin connection is a modular form. And here at higher genus, there's a more general notion of a modular group. It's SP to H, Z. And this F tensor is a tensor with respect to the modular group. So this is just a conversation starter for those who want to hear more on this after the talk. But to return back to the main storyline with the goal of defining polylogs, I should proceed to giving you the higher Fs. What about F2, F3, and Fn, and so on? And here is where we do even more convolutions. So using further convolutions of above, one can produce tensorial versions of the higher integration kernels here. And it's more or less the same recursion that I already wrote down at the genus 1. I can produce an F with an arbitrary number of indices by convoluting the Arakelov-Green's function against the derivative of Arakelov against a lower rank F tensor. And each time I convolute, I must specify which anti-holomorphic differential I mean. So in each step, there's one more index with each step of that recursion. Okay. And here you can check for yourself that if you specialize this to the genus 1 case, then you simply get back the Fn, which then, by translation invariance, only depend on the difference. Okay, we are almost there to assembling the flat connection, the generating function of higher genus polylogs. Let's remember how Brown-Levin were putting these things together. The Brown-Levin connection was essentially a generating function of the Fs decorated with some non-commutative variables. So what's the analog of that? So the generating function here employs a freely generated Lie algebra. So we had generators A and B in case of the torus. And morally speaking, A and B were representing the two homology cycles, A cycle and B cycle of the torus. And here at higher genus, we have more cycles and accordingly more generators. And they still are taken to obey no relation whatsoever. Okay, and it's in this freely generated Lie algebra that the connection will take values. And we build it as a generating series of these F tensors. And each time I go higher in rank, I need more adjoint actions with respect to the B generators. So let's introduce a capital B, which is nothing but the adjoint action with respect to the little b. So this is the same construction that you saw at genus 0, genus 1. The only novelty is that these generators carry indices. Okay, and now this object here has a nice differential equation, and this will be crucial to get a flat connection. So again, you can rewrite the anti-holomorphic derivative in terms of the same generating function. So there's adjoint B. And this is the key property to demonstrate flatness on the next page. And again, I'm staying away from the singular point. I keep x and y distinct. Otherwise, there would be a delta function. Good. Yeah, before writing down that flat connection, let me point out a special case at genus 1. I mean, at genus 1, that index is pretty boring, only takes one single value, and then it gives you back the Brown-Levin object, or more precisely, that Kronecker-Eisenstein series, omega. To be very precise, it also has a factor of b up front. But the funny paradigm shift is, if we could treat this b as a commutative variable, back then at genus 1, there was a single B generator, which clearly commutes with itself. But now there are several such B generators. So it's, if you wish, a non-abelian version of that. Okay, now before time is up, it's time to deliver the punchline with the final construction of the connection. So this is the main result of this paper from last year, June. So a flat connection, which closely follows the Brown-Levin connection, goes as follows. There is a little bit of dx bar. I mean, you already saw this at genus 1, so it's probably not a surprise that also its higher genus uplift makes reference to anti-meromorphic stuff. And now the dx component is given that by that object psi that I just introduced, full of convolutions of the tensorial F kernels. And it acts on the other generator A. It was also like that at genus 1, where this series here acted on the generator A. Now the new thing is that there are several such A's. And okay, here's a kind of formal addition term. This is something which at genus 1 is easier to hide, but which is needed in order to get a smooth limit to the Brown-Levin connection. So if you don't like that, just call this quantity A hat and you can still proceed. But this is more to be manifest that this specializes correctly to Brown-Levin. More precisely by what you saw on the other blackboard. This part here will, in the genus 1 instance, degenerate to specialize to this driving force of the Brown-Levin connection. Okay, yeah, and the flatness is an immediate consequence of this anti-holomorphic derivative over there. So that's why I was stressing the Laplace equation of the Taylor-Green's function. This is, so to say, the 0th order step in ensuring that the connection is flat. For every pair of points x and y, well, staying away from the diagonals, so don't make them equal. And as such, we can use it in a path-ordered exponential to generate homotopy invariant iterated integrals. So I guess the last step of reading of the polylogs is mostly a notational exercise. We do it in the same way as Brown-Levin did this at genus 1. This is a matter of expanding the path over exponential in all the non-commutative variables that could possibly occur. So clearly it starts with a trivial term from the 0th order term in the exponential, and then there will be contributions with a single A letter and other contributions with a single E letter. And yeah, for each of the coefficients is a polylog on its own right, and they have 3 indices. And one can even show good modular properties when checking out how different bits and pieces behave under the modular group SP to H. So again, if you want to have a formal all-order expression, you sum over all words W that can be formed out of these non-commuting letters, the little a's, and likewise the little e's. Yeah. Okay, so we need a word to label the polylog. It depends on a pair of marked points, x and y, that tracks over which path you have integrated. Sorry, it tracks the end point of the path, and you can go in any way you like from y and x, as long as you don't cross the poles. And what I'm not spelling out, it also depends on the moduli, these period matrices. You probably saw that I got lazy 1 or 2 blackboards ago, I think already for the Arkelov-Green's function. I didn't say it explicitly. It all depends on the period matrices. Okay, it's these gammas about which we claim that they are closed under integration, and which I hope that in one way or another, they will be in the future useful for other areas, maybe primarily Feynman integrals, but let's see where else. Good. Yeah, this was meant to give you a sample of how certain ingredients of string amplitudes can be inspiring to find a mathematical description of iterated integrals, which is quite close to what people like Brown, Levine, Enriquez, and Servini did. And yeah, I hope that more and more can be learned by staying in dialogue in between the communities of string theorists, particle physicists, and mathematicians. Good, that's it.
Very last sentence of your book. Can you comment on which Feynman integrals you think could be connected to this?
Yeah, absolutely. So this is with massive internal lines throughout the non-planar double box. It was for a while under the suspicion to be genus 3, some paper of Gorgudis and Sun from perhaps 10 years ago. But last summer, it was verified by Weinziel, Page, Pöbel, Matsuka that in truth, it's a genus 2 curve. And a similar genus drop was observed in a 3-loop integral, something like that. And again, internal lines with generic masses. There, an initial suspicion was genus 4 or 5, but in truth, it drops. It ends up being, I think, genus 3, but I'm not exactly sure.
But I guess there's no simple connection between the genus of the Feynman diagram and the pictures you're drawing, the string.
Oh,
Because I might have thought, you think of this field theory as a degeneration of string theory. And you'd be able to have a more direct connection, but I guess it's not that simple. Or...
Yeah, as far as I can see, it's not. As you say, in string theory, you start out integrating over the surface, but there's furthermore a loop momentum, like the zero mode of certain worldsheet fields. So working at fixed loop momentum, you integrate over the surface, but you're later on integrating over the zero mode. But if you want, you can integrate over the zero mode first, but in one way or another, there is a loop integral baked in these string theory calculations.
But I guess the connections are now, in a sense, observational, in the sense case by case, that you analyze a Feynman integral, then you say, oh, I can see it's connected to one of these functions. Is that?
That's right. Yeah. At the beginning, it's at the level of case by case studies. Some groups are working on the banana family with Calabi-Yaus of higher and higher dimensions. And then, yeah, These are some examples of higher genus Riemann surfaces. And yeah, it's really important to canonicalize the functions in order to see such genus drops quickly, to avoid making your life unnecessarily complicated. One never knows if something looks like a combination of Calabi-Yau periods, perhaps there's some conspiracy and it's later on something simpler. That's why we
in this setup, would you see this drop in your language?
No. So we are not yet there to represent these Feynman integrals using the polylogs for the following reason. Here we have some intrinsic non-holomorphicity in the description. And at genus 1, this is pretty easy to gauge away and to connect with the gamma twiddle functions. And those in turn were connected to the polynomial description by a duodine. And now at higher genus, well, you can again look at the hyperelliptic divisor where a polynomial equation defines the surface. And I don't know yet how to relate this hyperelliptic description to, say, a Markelov-Green's function and integration kernels. And one of the difficulties is to first go holomorphic. So our first goal is to find a messenger object, a meromorphic connection built out of prime forms and other stringy objects. And then, as a second challenge, one would need to connect these prime forms with a hyperelliptic description. Yeah, work in progress. But one bonus property to these objects, we are not relying on a hyperelliptic description. I mean, starting from genus 3, not all of these surfaces are hyperelliptic. And it's a 5-dimensional space of hyperelliptic genus 3 surfaces, but a 6-dimensional space to which we have access with this construct.
Is it known to detect whether a Feynman integral would reduce to a Riemann surface as opposed to a Calabi-Yau?
Oh.
Is there some sort of rule?
Not aware of any. I'm sure many people are thinking about that at the moment.
So if you have a Feynman integral, you can write the differential equation for it. I mean, that's a big hit. But then you should be able to look at the Fuchs operator for that integral. That should be able to tell you something. Like in some cases, like in our scenario, there's something where some person from mathematics is able to say that a particular Fuchs operator that doesn't factorize further, like corresponds to some Calabi-Yau. So that's like all the other things that you hear people toss around, oh, they can't, and yada yada yada. I think there's always these issues. Oh, is there maybe a change of variables that makes it similar?
Yeah.
And so that is mostly heuristics, I would call, but and often, yeah, it's sometimes the things are simpler than we thought.
I mean, it's sort of remarkable that for Seiberg-Witten theory, which is very different from all this, but that you can actually always, for all the known gauge groups and representations, represent this in terms of a Riemann surface. Didn't have to. And yet, you know, all practical cases are like that. I don't think there is a general proof there either, but there it just happens to be true. I mean, for all cases, no.
I see. Okay, like heuristics pushed to a very, very high level.
Mhm.
Okay, I see.
Right.